I'm going to have a look at trying to work out how close a close nearby star is, and we're going to use a parallax method to try and do this. What is parallax? Well, the way of doing that is to simply put your thumb up towards something and you look at the background, and now you close one eye and then you look and close the other eye, and you'll see your thumb moves. That is parallax. What I see as I open one eye and close one eye is the image moves. But we need a better experiment to try and do that. So let's see if we can set up an experiment, and this one can easily be done at home. So let's see what we've got. What I've got here is a board. Now on this board I've got some squares. You can do this with any piece of something like A3, A4 paper, and just put a few lines on it. That's all you want. You've got to look at something to see that it's actually moving. I've got a little ball here. This is just a little rubber ball, and I've stuck it onto a pencil, and I've stuck it onto my surface with a bit of blue tack, and I've got a meter rule here just to give me some idea of where it is. So I've placed this about 25 centimeters away from my background, and some 75 centimeters further along I've put a torch. Now mine's held in a retort stand, you can hold yours, and what we've put is, because I can't manage your eye terribly well, we put a camera here to represent your eye. Now to get all this working nicely, what I'm going to do is I'm going to turn some of the lights off. That makes it harder for you to see until we turn the torch on. And now you can see we've got the torch shining on. This is a representation of my star, and we can see where my star is in relationship to the background. Now let's see what you can see. So I'm just going to put a different camera on for. Right, we have a little problem. Ready? So the world goes round the sun, the Earth moves slightly. So let's move the Earth slightly. And what we're seeing is, can you see the star moving against the background? I'll try and angle it a bit better. So if I look, we can see where the star is, this ball is. Not necessarily the shadow, but you can also apply it with the shadow. And we can see that that ball is moving very slightly. Not much, but it is moving very slightly. If we want to look at it a different way, we could actually just move the light. That isn't the way that the system's actually working, but we could see that if we do actually move the light, we can see the shadow moves as we move the light. So we've got here the camera moving, And if I just look at the camera moving, you can see that what we're doing is just moving the camera across very slightly from one side to the other. So let's imagine that the camera is the Earth and this is the winter. The light represents the sun, and this is a nearby star we're looking at. We'll give it a name, we'll call it Bernard. And we've got a nice name for the star, and we can look at the stars in the background. And perhaps each of these little crosses could represent another star further away. I'm only working on a simple limit of what I've got. So what we see is, if you look at the camera, we've got some idea of where this image is. Now I could put this in front, and if we put this in front, what we can do is we can mark where this star appears on here. And I've got something about there. Let's take a picture again, but this time we're going to look at what happens in the summer. That was the winter. The Earth has moved around the sun and is now the other side of the solar orbit. Let's look at the camera. It takes a different view, and now I can measure out there where the star is. So I've got two measurements, and with these two measurements I can work out here how much my star has moved from the summer to the winter. I can do it more accurately, of course, if I use this square, but we can work this out. Okay, so what's next? I've got my measurement of my parallax. Now what we can do is we can see if we can work out how far that star might be from the Earth. So let's start with having a look at what really is going on with parallax, and this might give us some idea about what's going on. So let's basically draw out a model of what we've got. So in my model, what I've got is I've got the sun. That was represented by my torch, and I've got, going round here, the orbit of the Earth, and this is vastly exaggerated. I've got a problem with my ability to draw this. So we've got the Earth, perhaps let's say in winter, and we've got the Earth, let's say in summer. And that was me moving the camera from one side to the other. And we've got my nearby star, Bernard. And what we're looking at is a background here of background stars that are available for us to have a look at. Now, what we look at is this star from over here. And when we look at this star, we see this other star here behind it. Now when we look in the summer, and this is very exaggerated, we see that star is no longer in front or behind that star, but another one has changed. Now, these are basically so far away as to be considered fixed in position, whereas this star, which is relatively close by, we can consider it to be sort of moving against the background. Let's join up here. This angle here is our parallax angle. And if we know that, we can work out the distance to the other star. And we measure P here in arc seconds. An arc second, if you want to try and work this one out, is simply when we take our protractor and we can measure out something. So let's just do that. I'm just going to put my ruler on here, give me a rough basis. If I put this on 0, and then what I want to do is down here measure in 1 degree. So let's help myself a little bit, and I'm going to measure 1 degree. So that's 1 degree. It's not very much, is it? I'll go the other way. There, 1 degree. But as we get further and further away, this distance is simply going to increase. Now, this is 1 degree. Let's divide this 1 degree up into minutes. So that's going to be 60 minutes. And that 60 minutes we're going to divide up into seconds. And there's going to be 3,600 seconds in the 1 degree. And we are measuring here this. Probably we're measuring a distance like 1 or 2 arc seconds. So we're measuring down here to 1 to 2, sort of 3,600ths of a degree. So we've got to have some idea of how this works. So scientists came up with a unit, the parsec. A parsec is the fact that we measure angles here not in degrees but arc minutes and arc seconds. So we've just said there are 60 arc minutes in 1 degree and there are 60 arc seconds in each arc minute. So we know that 1 arc second here is 3,600th of a degree. Now we also know another distance. We know the distance from the sun to the earth, be it in summer or winter. And this distance here we call an astronomical unit. Some 93 million miles, I remember, distance from the earth to the sun. So we've got our parsec. It's defined as the distance at which the radius of 1 parsec will subtend an angle of 1 arc second. Let's draw that out. Here's our orbit around the sun. This distance here is 1 arc unit, and this angle, not drawn very accurately, I might add, this angle here is 1 arc second, or if you prefer it, 1 3,600th of a degree. So if I know that that distance from the sun to that star, that is 1 parsec. So if we've got a different distance, I can say that my distance is going to be 1 over the parallax angle, where it's measured in arc seconds. We measured our angle here, we measured our distance it's going to make. So once we've done that, what we've got is this distance here, that's what we measured on the board. And so what we could do is we could try to work out what that angle is. Now my numbers are going to be way out, because we're not looking at anything like a parsec, we're looking at a meter. So I can't actually do the calculation, we can just have a look and see what it is. And this gives us an idea of measuring nearby stars, but it only works with stars up to about 100 parsecs away from the Earth. Anything any more, even though we might be able to sort of manage to see it, we just cannot measure that angle. It's just too small. And I've exaggerated my system beyond all comparison. But I've done that so you've got some idea of how it works. So this is parallax. Now we meet this problem in parallax in other ways. And I'm just going to show you another way that we see it work. And this is with my very old camera. I'll take my ball out there. This is my very old camera. This is a twin lens reflex camera. And the idea is we open this top up. I look down here and I look down at a mirror and I look through this top lens. But the camera lens that takes the photograph is this bottom lens, and this one puts an image onto the film here. The problem I get with this camera is when I hold it and I look down, what I see when I look down is an image that's up here, but what I take a picture of is the image that's down there. And I have to cope with this idea of parallax to try and get this to work. And it proved so popular that these cameras no longer exist. They are wonderful in what they can do, but the problem is that a camera like this doesn't give you, let's say, WYSIWYG. What you see isn't what you get in this case. You're getting a slightly different image. So a camera like that really has gone the way of so much modern technology. It's sort of now no longer required. And instead we use a camera like this, which looks along here down through, in fact it's called a pentaprism, onto a mirror, and we look through the lens. And now what you see is what you get. The problem is with that to take the picture you've got to have a mirror and it's got to move out the way. And we can make a camera far more compact, picking up the example now with a typical little camera to take a picture. So this one is my favourite Olympus. Why? It's waterproof, ideal for English weather. On a typical summer's day I can take that out, and it's so much thinner because we've only got to worry about the lens going on to the charge couple device. We don't have to have the worry about putting a mirror on these bigger cameras, which is why cameras seem to be moving away from this design to cameras now which are going to be mirrorless. The technology has changed. A camera like this used to have a back that opened and there was the film. Now we don't need that. Technology changes, and with that technology out has gone the way of parallax with cameras like this, and it's a problem now that doesn't exist. But by knowing about that, scientists were able to work out this idea of parallax and the star moving. That's one way of trying to work out how far a star is away from us. We can simply look at nearby stars and we can work out that basically if they move in front of the stars behind them because they're very close, then we can measure them. But how about the stars that are further away? How do we measure those? This becomes much more of a challenging problem. How about even further distances? And this was a problem that Hubble met a long time ago, somewhere in the sort of 1920s, and in our galaxy, as our star system, as we looked out, he could see some fuzzy shaped objects. Other people had seen them. He investigated them. And these fuzzy objects were given odd names. So we had something called, on the catalogue, Messier systems, and some of them had interesting sort of names. And he looked at an object, a nebula, called M31. Messier's number 31. And there was a lot of arguments. Some people said it was inside, it was just sort of a star cluster inside our galaxy, and other people said, oh no, this is actually a galaxy, it's a long way away. So he needed to sort of find a way of doing this. So he looked at certain stars, and these certain stars have a known brightness. So if I look at two stars, so let's just have me looking out here at two stars. I've got this star here and I've got that star there. Now from the type of star I know what its brightness is. I've got this star here, and yeah, you can't see that one, it's that far away. Let's bring it into so we can see it. So this star, perhaps we're lucky enough to know how far this star is away, and let's suppose we say it's going to be 50 parsecs away, and it's got a brightness of 1, whatever that unit can be. We look at another star which is exactly the same type, and we find this brightness now is only a quarter of that one. Now we have a rule which is called the inverse square rule. And that looks something like this. Now, let me try and draw out this idea. Let's divide this one up into 4. And if I've got everything correct, that's going to go through there. Right, so this is my inverse square law. I have doubled the distance, so that's 1 times, that's going to be 2 times, and you can see that my drawing is not anything like accurate. And what we've got is this area now fits in just to that area. So it's got, when we've doubled the distance, we've quartered this. So if I look at my star, if I've got a quarter of the brightness, then I know I've doubled the distance. So this is now 100 parsecs away. Very simple example. And what Hubble did, he looked at a local star, and he looked at a star in this galaxy here. And what he found was it was quite a lot dimmer, and he measured how bright that star was, and so he could work out the distance of this, and he showed that these things were far, far away, much, much, much further than our galaxy, that they actually lay outside of our galaxy. And so this was a galaxy, and it wasn't a nebula, just a cloud of gas. So he showed that these galaxies lay outside of our own galaxy. From this, Hubble could actually work out various bits and pieces, and from his observations, Hubble came up with the fact that here the velocity of the galaxy equals some number, and we'll call this H0, called the Hubble constant, times the distance, because he'd worked out the distance, and now he needed to work out the velocity, and that he did by looking at redshift. Now, to explain redshift is more difficult, to sort of have some idea about the Doppler effect. And the Doppler effect really requires a whole video on its own to go through and show the Doppler effect and how everything works, and how blue shift works and how red shift works. So I'm going to leave that one and just accept here for the moment that he measured the distance to the galaxy, and from this he could actually work out his Hubble constant, which he found to be true for all sorts of stars. Now, when we measure the Hubble constant, then we get some interesting things. So the Hubble constant, its units are interesting. We measure the distance, the velocity in kilometers per second, and we measure its distance using something really quite horrible, which are not parsecs, but we have to use megaparsecs. Kilometers per second per megaparsec. So let's suppose he measured a galaxy. So let's choose a galaxy. And we've got this little galaxy, and let's suppose it is 300 megaparsecs away. Now with this he can also work out various other bits and pieces, and what he could also measure is its redshift. More about this when we do Doppler. And this redshift Z equals 0.0, let's say 60. What do I know? Well, we know that this redshift equals the change in velocity compared with the speed of light. So I can work out here from 0.06 equals my velocity, which is what I want to work out, divided by the speed of light, which we're measuring in kilometers per second, which is 3 times 10 to the 5 kilometers per second. Let's go and do this on the calculator. So on my calculator I've got my 0.06, and I'm going to multiply that by 3 times 10 to the 5. And that's going to give me a velocity of my galaxy, which is here some 18,000 kilometers per second. That's moderately fast, I suppose. You know, I've been at 70 miles an hour, sort of 120 kilometers an hour. That's quite a lot faster, isn't it? So let's work out now various other things we can work out. So I may want to work out what this Hubble constant is. So I can work out my Hubble constant simply by taking my V is my Hubble constant times the distance. So I can work out my Hubble constant is going to be my velocity divided by my distance. And all we have to do is simply work out what that is, and it's not a difficult sum because I've deliberately chosen easy numbers to give me a Hubble constant here of 60, which is not right, kilometers per second per megaparsec. I'd be sacked by Hubble because that's nothing like the Hubble constant. But we need to try and work out what something's going to be so we can actually work out how old perhaps the Earth is. Now, what do we know? Well, we know that the Hubble constant actually is about 2.3 times 10 to the minus 18 . So let's assume that the Hubble constant is in fact constant, then we can actually work out the time for a galaxy to sort of move away from us, and this is called the Hubble time. And if we play around with this, because we know that time is going to be distance divided by velocity, so therefore time here is going to be 1 over the Hubble constant. Now if I know that, we can go back in time to work out some values. What I could work out is that 1 over the Hubble constant, which is 1 over 2.3 times 10 to the minus 18, that gives me a number, and that's going to give me 4.3 times 10 to the 17. If I take that number, my 4.3 times 10 to the 17, and we divide that by 365 days in a year times 24 hours times 60 minutes times 60 seconds, then we should get an age of the universe. So let's do that. 4.3 times 10 to the 17 divided by 365 times 24 times 60 times 60. And the age of the universe comes out from my calculation as 1.36 times 10 to the 10 years. So we've got an idea that the universe is about 13.6 billion years old. Maybe it is, and maybe it's not. We do have a few problems, and I'm going to leave you with a little problem to think about. Quite a few years ago, an astronomer, Vera Rubin, was looking at some galaxies. And these galaxies were spinning. So she looked at the rotation of these galaxies. At that time it was thought that the gravity of the stars within the galaxies were the only force holding the galaxies together. Now she observed the light and the motion of these galaxies, and she could calculate the speed at which these galaxies were rotating. But there's a problem, and the problem is by comparing the force of gravity to the star's rotation, it was a problem. What she worked out was there wasn't enough gravity. So instead of staying like this, what would happen is the galaxy would actually look like that. Literally flying off into space. So the way of getting round that problem was to reckon that there had to be something stopping them to do that, and this is called the galaxy rotation problem. Now there are three ways that you can fix this problem. You could say that number one, we may have gravity holding it together, but plus something else. The second way of coming up with this problem is basically to decide, well, okay, when it becomes big, Newtonian rules sort of, well, they just break down, they just don't work. And the other one could be that was, well, there were large amounts of matter basically missing. If there was a lot more matter, then this would work. So one of those is probably right. So we've got to try and decide whether there's something else working besides gravity, whether Newton basically got it wrong, or whether there is something else out there. And if there's this large amount of matter that we can't see, touch, taste, feel or anything else, let's panic a minute and let's give it a name. Oh, I don't know. What's your fancy? I haven't got a clue. Let's call it dark matter. Now, this is the most popular idea. And we know there's got to be at least 6 times as much dark matter as there is ordinary matter. In fact, really, we're reckoning on matter equaling at only about 5% is what we know about. So what's left of this 95% is going to be something else that we don't know, that we can't see, we can't smell, we can't taste, we can't detect it. And every means we've made so far to try and detect dark matter has actually failed. Now that could be because it doesn't exist. Or it could be that we're just wrong. Maybe it'll be up to you to find that out. Next time we'll have a look at Doppler. We want to look at things like redshift and see if we can understand what's going on. So until then, I'll see you next time on A-Level Physics, going through topic by topic. Stay safe. Bye bye.